Hello and welcome to Efficiently Explaining Constraint Satisfaction Problems with Unsatisfiable Subset Optimization. My name is Emilio Gamba and this is joint work with Bert Bogas and Thias Guns from the VUB and KU Leuven in Belgium. You are probably familiar with constraint satisfaction problem. One example is the logic grid puzzle, where given a set of clues, you have to match a certain number of entities of different types with each other within a logic grid. Another example is the Sudoku puzzle, but more important applications are scheduling problems, configuration problems, and planning problems. But how do you go about at explaining the solutions of a constraint satisfaction problem? Before I tackle the main contributions of this presentation, I will first sketch some context and briefly explain the motivation behind our work. Then I'll answer the main question on how to generate an explanation sequence for explaining the solutions of constraint satisfaction problems. And for that, I'll introduce the concept of OCUS and an algorithm to solve it. We will see that our approach indeed improves the quality of the generated explanations and will conclude with some prospects on future work. Let's first start with some context and the motivation. In our previous work, we formalized the stepwise explanation problem, which it works as follows. So we have a formula which is a representation of the problem constraints and a solution that satisfies the constraints. The goal is to generate a sequence of simple explanations that explain step by step how to derive the facts of the solution. Here, simplicity of an explanation is measured by a cost function. To compute an explanation of a fact, we rely on extracting the minimal unsatisfiable subset of the formula and the negation of that fact. So, how do we generate a new explanation at any given step in our explanation sequence? Well, for that, we have to compute a mus for each of the remaining facts and then select the best one we can find, and this is the best explanation we can find at that point. What we see here is that the cost function is not encoded in the mus computation, but in the explanation finding heuristic, and there is no guarantee that the non-redundant explanation is provably cost optimal. This last remark has motivated our work, namely that explanations are not optimal, but they are heuristically found. So mus guarantees non-redundancy, but not the quality of the explanation. An alternative would be, for example, to use the SMUS algorithm, which guarantees cardinality minimal explanations. So the question is, how do you guarantee provably optimal explanations? The next thing is that explanation generation still takes a lot of time. Is there some way we can avoid looping over the literals when searching for the next best explanation? And finally, can we reuse information from an explanation call to another? For that, let me introduce the concept of optimality. So, how do you guarantee optimal explanations? Well, we transform a mus problem into an optimal unsatisfiable subset problem. Namely, you have to find a subset of an unsatisfiable formula, and this subset has to guarantee to be optimal. Namely, you cannot find a cheaper one that is also unsatisfiable. So our mus calls are replaced by OUS calls with respect to a given cost function, and we select the cheapest explanations that we can find, and this constitutes the next best explanation at any given step in the explanation sequence. The next question we would like to answer is, can we avoid looping over the literals when searching for the next best explanation? Of course we can. And what we see here is that all these calls are relatively similar to each other. Is there some way we can exploit this? Well, the goal is still, the task is still the same. Namely, we have a formula and the negation of all of our facts, and we have to find an unsatisfiable subset of this which contains exactly one negated fact and remains optimal with respect to a given cost function. Why do we specify the exactly one constraint? Because we want to explain one fact at a time. So the OS problem becomes now the OCUS problem. So you are given an unsatisfiable formula, a cost function, and a condition the unsatisfiable subset must validate, for example, the exactly one constraint, and we call a subset of our formula an OCUS if it is unsatisfiable, if it validates the constraint, and there does not exist another subset which is cheaper in cost and that also satisfies the constraint. So that now that we know that we can compute OCASes, our explanation or computing the next best explanation at any given step is now easier. We specify the exactly one constraint and we compute the OCAS on our formula with respect to our given cost function and the exactly one constraint. But how do we effectively compute optimal constraint satisfiable subsets? Well, our OCUS algorithm is a heating set based algorithm, which means it relies on computing minimum heating sets. And for that, let me quickly introduce the minimal heating set problem. So we have a set of elements, and we have a collection H of sets of those elements called sets to heat. The goal is then to find the smallest heating set such that every set to heat is hit at least once by an element of the heating set. For example, let's say we have the following heatings, the sets to heat, namely H1 to H4. We can compute a number of heating sets, namely C1, C2, C3. We can see that C1 hits H4, C2 hits H1 and H3, and C3 hits H2, which means that the heating set hits every set to hit and by at least one element of the heating set. Now, let's modify our problem and add weights to our elements. The goal is mostly the same, but now we want to find optimal heating sets, such that the heating set is now with minimal cost. Our previous heating set C1, C2, C3 now has a cost of 7. Is there another one we can find that is cheaper in cost? Well, for example, you have C3, C4, C6, C8, which hits all of the sets to hit and which has a cost which is lower than C1, C2, C3. That means that it is a better heating set, and in this case, it's also an optimal heating set. Before I tackle the OCUS algorithm, let me quickly introduce minimum correction subsets. A correction subset is a subset of an unsatisfiable formula, and if you remove that part from the unsatisfiable formula, it now becomes satisfiable. The remaining part that is satisfiable is called the satisfiable subset. If you cannot remove a smaller correction subset, such that the remaining is still a satisfiable subset, then it is also called a minimum correction subset. So our algorithm uses this concept in the implicit heating set duality between minimum correction subset and minimum satisfiable subset. Namely, that if you compute a minimal heating set of a minimal unsatisfiable subset, then you have a minimum correction subset. And if you compute a minimal heating set on the minimal correction subsets of an unsatisfiable formula, then you have a minimal unsatisfiable subset. So we extended this ID to OCUS to compute OCUSes. So our algorithm works as follows. We have a collection at line 1 of sets to hit, which are going to keep track of our minimal correction subsets. So if we hit this collection of minimal correction subset and it isn't satisfiable, then we have a mus, and if in this case it's going to be an OCUS. So at line 3, we are repeatedly going to compute hitting sets until we find an unsatisfiable one, and if it isn't satisfiable, it is a ocus. If not, we have to grow our hitting set as much as possible, which means that we add as many constraints as possible while it remains a satisfiable subset. And then when we are done, we take the complement of it and we add it to our collection of sets to hit, which means that we just added a new minimum correction subset. What we see here is the question that we now want to answer is, can we reuse information from an explanation step to another? Well, what we see here in our algorithm is that we have that we keep the most important data structure that we can keep track of is the collection of sets to hit. Namely, we know that every set in the collection of sets to hit is the complement of satisfiable subsets. So if we keep track of the set of satisfiable subsets, that means we can bootstrap at a later time our collection of sets to hit by the complement of the satisfiable subsets. Now, before I tackle how our algorithm performs, let me quickly summarize what we saw up until now. We saw that we can guarantee the optimality of the explanation and that we can take advantage on the structural constraints, the form of the structural explanation in order to improve the efficiency of our problem. And next, we see how we can reuse information between an explanation call to another. So, in order to validate our approach, we tested our implementation on a set of logic grid puzzles. What we can see here in this heat map is that at any given explanation step, we compute an explanation with our OUS-based algorithm compared to a naive mus-based explanation. And we can see that the quality of the OUS-based explanations is much better than a mus-based explanation. In the following graph, we compare the runtime of different grow configuration. We can see that using the appropriate grow configuration highly impacts the runtime for computing an explanation sequence of all the puzzles in our OCUS algorithm. In the last graph, we compare the OCUS algorithm with the optimal unsatisfiable subset algorithm. So we compare the two with the baseline, which is the naive mus algorithm. So what we can see here with the red and the green lines is that computing an explanation with the constraint version, we can quickly find some explanations in the beginning of the sequence, but in the long term, OUS-based explanations are much more effective thanks to incrementality. So, to conclude, we have introduced the OCUS optimal constraint satisfied subset to explain how to solve constraint satisfaction problems. And for that, we build onto three ideas. First, we guarantee that optimality of the explanation to find better, simpler explanations. Two, we take advantage of the structure of the explanations to help our search towards the next best explanation. And three, we reuse information between successive explanation calls to improve efficiency of our algorithm. There are still some open questions remaining, such as what is a good cost function to quantify explanation difficulty, to how do we extend our approach to explainable optimization to answer different types of Y queries, which is very related to explainable AI planning. And three, how can we effectively scale our approach using approximate algorithms as well as search for incremental algorithms to answer the different Y related queries. Thank you for listening, and if there are any questions, I'll gladly answer them at the Q&A session.